Hi everyone, I am Dr. Jaya Bhatt. I am a postdoctoral research fellow at Indian Institute of Science, Bangalore, India. In today's talk, I'm going to talk about impact of global warming on probable maximum precipitation, which is also named as PMP, those estimates in India. Well, PMP estimates are essentially required or desired to arrive at the design flood that is utilized uh, to construct large dams or critical infrastructures. Here, at the bottom of my slides, I've kept few of the pictures that of the large dams that we have in India. And if we look at over the years, if how the number have evolved, we see there is a sharp increase in the construction of dams from 1990 to current. And till date, we have more than 6,000 large dams. Either those projects are ongoing or about to complete or completed projects. So, what is concerning here is, as we all know, these dams are constructed so to meet the demand that is there by the growing population or due to the development that is happening. But then we have to be and we have to ensure the safety of such structures. And if we look at what has been the history of the dam failure, we found that hydrologic or flooding is the major cause of or the major driver of dam failure, whereas these failure could result into catastrophic consequences. It could for society at large, not just for economy, for people, for economic conditions as well. So there's severe damages that happens because of failure of such critical infrastructures. So conventionally, what has been done is these structures are designed corresponding to the flood that is triggered by probable maximum precipitation. So what it is the theoretical maximum precipitation that can occur at a place. So we are looking at the what is the upper limit of the precipitation? Since there is no such quantity that exists, and that is one of the challenging to arrive at PMP value, that is the theoretical quantity. So we have methods in place to arrive at the estimates, but this challenge becomes much more bigger when there is ongoing changing climatic conditions. Because as we all are aware, over the years, the precipitation, even in last recent past, we've seen extreme precipitation becoming much more extremes. That is due to the increase in temperature leading to saturated vapor pressure, saturation of vapor pressure in the atmosphere and leading to high rainfalls. So this would would also be the driving force to see if the upper limit itself would change, not just the precipitation. If its upper limit is changing, that would lead to change in probable maximum precipitation. So there is a focus and also drive towards estimating these values, and a lot of research in recent past is now devoted towards improving our conventional methods which are there in place to estimate PMP values and incorporate changing climatic conditions to arrive at non-stationary PMP estimates. So here I'm going to tell you what is the underlying rationale behind calculating PMP using one of the widely used method called moisture maximization. So we look at the historical storm and see what is the corresponding precipitable water which led to the precipitation depth from this storm. And then historically, maximum precipitable water is then looked up, and we maximize the historical storm to its upper limit by using the climatological maximum value of the precipitable water. So usually we don't have data corresponding to precipitable water available, and we use dew point temperature uh, as a proxy to arrive at the estimates of precipitable water with the use of this method. But all this works under stationarity assumption, meaning that the climate is not going to change over the time. So the maximum limit that we are assigning to the dew point temperature here, or the corresponding precipitable water, may not change. But that's not the case. When we're looking at the uh, PMP values in future, it is highly likely that the magnitude of the variables which derive the precipitation phenomena would itself increase, and hence the precipitation will increase, and leading to the PMP may also increase or decrease or likely change and may not remain what we have derived previously. So towards that, there have been research done in the last decade wherein people have come up with options or strategies to improve the conventional methods to arrive at the PMP estimates inclusive of changing climatic conditions. So there are simple strategies which have been used that I'm going to name as variants of non-stationarity. So herein I'm looking at three variants. And the first variant is we simply look at the trend in the projected data of dew point temperature. So whatever trend that we found, one can incorporate it into its maximum value, and that would be utilized further in the conventional method to estimate PMP. Other way is one could use a fitter statistical distribution and consider the trend not just in data but in the parameters of the distribution. So that is the variant 2. And in variant 3, what people have looked at is uh, we constrain the data to such that it makes a stationary window of the data. Consider the stationary situations of the climate for that particular window, do all the computations, and then keep moving with the window being moving over the time. So it would be a sliding window. So I would be looking at what is the difference that we arrive at when we go with the stationary model-based PMP or when we utilize the non-stationary model-based PMP, wherein we're using the projected climate data and incorporate the changing climatic conditions into the estimation, how much is the difference that we arrive at for the estimates. So in this case study, I've looked at 24 subzones over India, and these are hydrometeorological subzones, which are the smallest unit on which we arrive at design floods. So for use in this work, I've utilized precipitation, temperature, and relative humidity information from various sources which are available. For observed data, we've used something which we have available in India itself. Indian Meteorological Department supplied this information, and relative humidity uh, from the reanalysis data I've utilized. But for projections, what I'm looking at is the data, the projections of relative humidity and temperature. I'm looking at from the 11 models, 11 climate models. And for all four socioeconomic pathways, I'm conducting the analysis to assess where the increase is significant or not. So these are the list of the models or climate model data that I have utilized. All this has been processed and bias corrected with the observed data that we have and regraded everything to a 1 degree resolution. So we did some preliminary analysis to assess if the trend that we are expecting in the dew point temperature uh, is it really significant or not? So we looked at, performed a Menken-Dahl test, and we found that more than 70% of the grids that is there in over the zones in the India demonstrate a significantly, a statistically significant trend. So our hypothesis to go about with seems to be in line with the data as well. And here I'm going to show you the results. So, first of all, what we're looking at this bar graph here, the information that we obtained from 11 climate models uh, that has been utilized in the form of multi-model ensemble mean value rather than using only one climate model. So, here I am testing if how far in future I have to look at when the difference between the estimates that we get from the stationary based PMP and non-stationary based PMP differ significantly. So as you can see, if we move from a lower emission scenario, that is SSP1, towards the higher SSP5, more and more subzones are showing that an earlier difference is being noted. And it increases, of course, it is get and yeah, the results are not consistent for all three variants that we have discussed because they utilize underlying assumption on which they are based or the way they take the information differs. So prominently, whatever output I'm getting from variant 3 seems to show very early differences than for the variant 2 and variant 1. So then we look at what is going on with each of these variant. And here I'm showing you results for one of the subzones lying in one of the major river basin in India, that is Ganga. So the output here, the lines here, the colored lines correspond to different SSPs, and the black line correspond to what we have the stationary based estimate. And how much is the relative change that you could see on the right side on the secondary axis, and PMP values on the left side on the primary axis. So from each variant, first of all, I'll discuss first variant. There is a linear increase we can see as for each year, the PMP value is increasing. And that's because we have taken the linear trend information incorporated while computation. In second variant, we are utilizing the trend in the parameters. So for this study, I fitted a generalized extreme value distribution with a trend in location parameter, trend at the covariate is time. So it is also more or less similar to the previous one. However, the relative increase is much more higher. And for the third one, where we were getting very high values, very initial period, these are when I consider a sliding window and fit a stationary distribution and do the same analysis what we conventionally does and keep moving the window. Consistent to all the three, what one could say is there is an increase and the values are higher. However, which one is better or not, that has to be, and which one to use, that is again a question to be answered. So with all this analysis, what we could say is there is an underestimation of PMP when we use stationary based methods. So with all three variants of non-stationarity methods that we have used, we can say that more and more subzones exhibit significant differences when we compare the two PMP values, and it is much more higher or prominent for high emission scenarios, where such findings are more or less expected, but when we see with the data, becomes much more confident. And towards the end, wherever we need to put in efforts or assess the flood risk on those subzones where we do see consistent increase or the difference, significant difference in near future from all the variants, that has to be then further looked at. And with this analysis, what we are not done yet is still need a robust methodology, which could actually take in the physics of the phenomena and give us the option to account for changing climatic conditions, and yet arrive at the robust PMP values that one could use to reevaluate the increase risk or decrease risk if there is to our major or critical infrastructures. Um, with that, I would like to wind up the work, and I would like to acknowledge my professor, PhD supervisor, Professor V.V. Srinivas, with whom I've done this work, and one of my research group colleague who has helped me with the work, Dr. Anubhav Goyal. So thank you very much. If you have any questions, floor is open.
Thank you, Jaya. I did see a question. There's a hand up. I think it's Leon from Leon Hermansen. Do you have a question? Oh, they've lowered their hand. Okay. I've got a quick question. You've said that there's still work to be done to develop a more robust methodology, but presumably the idea is that this could the work that you're doing could be used for. Is it going to be used by like local authorities, for example, or regional governments to start mitigation planning now, for example, to especially I guess if you can plan for them, if you can mitigate now for extreme scenarios, then that's like a good idea to get that underway as soon as possible. I would assume.
Eh, Yes, yes, for sure. Whatever work we've shown here, that could be used as the primary or preliminary assessment to see which all areas are highly prone or risk prone, and start working with because the structures are already there in place. So we have to devise emergency plans, some mitigation measures. Meanwhile, when we get the very confident estimates, but this kind of statistical analysis that we have done could also serve for to get things started. Yes.